develop this compound with meta-aminobenzoic acid and NN dicyclohexyl urea. The compound formed a duplex stabilized by intermolecular hydrogen bond, and then we replace one of the hydrogen with a bromine, a heavy atom, and what we figure out that with bromine now there is a CO-Br halogen bond, and due to that halogen bond and heavy atom effect, so the compound is now showing phosphorescence. And so we have studied with all the solid and solution phase and microscopic and spectroscopic technique, and that the compound is showing phosphorescence at room temperature, which is very rare for an organic compound. There is no metal or nothing else, it is purely organic compound. And then we thought maybe the iodine will have higher impact, maybe the phosphorescence lifetime will increase, and so we replace the bromine with iodine, but surprisingly with replacement of iodine no halogen bond and the compound is not phosphorescence anymore. So like this change from proton to bromine to iodine, there is huge impact on structure and function of the compound. And then we have developed a larger version of the foldamer, so with 2 meta-aminobenzoic acid in the chain, and from solution state study with NMR, 2D NMR, and then temperature dependent NMR or solvent titration of DMSO-D6 in CDCl3, we figure out that the two compounds are different folding pattern in solution. We have also got the crystal structure of both the compound from CDCl3, and from where we can see that when the foldamer is shorter version, so this is a dimeric structure through intermolecular hydrogen bonding interaction, and finally in packing diagram these are also forming a honeycomb like structure. But for the longer version, when we have 2 meta-aminobenzoic acid residue in the sequence, so actually it forms a duplex double helical structure, and the double helix is stabilized by intermolecular hydrogen bonding interaction between 2 strands as well as pi-pi stacking interaction from the aromatic moiety. And so this is the packing structure of the compound in chloroform. But when we change the solvent from chloroform to methanol, from different solution study, we came to know that the foldamer is now folded in a different manner. In chloroform it was showing double helical structure, but in methanol now it is showing anti-parallel beta sheet like structure. So we believe that it is not only the molecule, it is the environment that also has huge impact on the structure and function of the material. So then we develop this compound, a peptidomimetic, and so the compound contains 2 amino acids, one is the leucine and another one is the tyrosine, and there this is a diacid. So we put both leucine or tyrosine in both sides of the diacid, and in a third compound we put one side leucine and one side tyrosine. So with the leucine the compound is completely crystalline, so we have the crystal structure. With tyrosine the compound is solution, it is a liquid, but when we put one side leucine and one side tyrosine, the compound is highly viscous material above 20 degree centigrade, but below 20 degree centigrade it can make a kind of fiber. And so this is the natural spider silk on my window pane, and this is what we have prepared using a spatula, or even you can use a injection syringe and you can do that at below 20 degree centigrade. And also we have studied the morphology of the compound, optical property of the compound using polarized optic microscope, and where we have seen that both the compound are synthetic material and natural one, they are showing the same behavior. And we have tested with this rheology and then the morphology by FESEM, field emission scanning electron microscope, so which shows that the compound is actually fiber like nature, and that fibers, if we zoom it, it actually made of small fibrils. So the fibrils are entangled to make the fibers, and that fibers can take some weight. So this is what. And then we have studied the structure of the fiber by using FTIR, NMR, and obviously the X-ray structure. And what we feel that the compound is from anti-parallel beta sheet like structures, and that helps to make a higher order assembly, a higher order packing, and that making the fiber. So fiber is strong enough to take certain amount of weight, and this actually mimicking the natural spider silk. And then we have developed a Juiter ionic spirocyclic Meisenheimer complex, and this is basically to remove all kinds of cations and anions from water. So, this is the compound which is very simple. So, we have just added picric acid with this DCC NN dicyclohexyl carbodiamide, and immediately it forms a spirocyclic Meisenheimer complex. So, where we have both positive charge and negative charge on the compound, as well as there are hydrophobic moieties. So, the positive charge on the compound will attract the negative charge from the water, and the negative charge of the compound will attract the metal ion from the water, and this hydrophobic part that will actually collect the other hydrophobic pesticides or herbicides or any organic moieties from the water. And by the way, so this compound, if we treat with water, it can clean the water and it's remove any kind of contamination from the water. So, we have started with all kinds of metal, and we have seen that it is working very well. And then we use this compound for removal of oils and organic pollutants from water also. And so, we have tried with various kind of organic compounds that generally pollute water. It's starting from different kinds of oil to benzene, toluene, xylene, etc. And we figure out that actually this compound is working fine. And then we have developed a device out of this compound, so to clean up the water or household water. So, how we develop these things? Now, we have just used a kitchen sponge, the sponge that generally we use to wash the utensils in the kitchen, and we have coated that sponge with our compound. And now, if in contact with the oil water mixture, the sponge is actually allowing the oil to pass through, but it's just stop the water to pass through. And so, with the oil water mixture, we have added a pump here, and so it's separating the oil from top of the water very nicely. And so, by that way, we can use this sponge to clean up water that contain other metal and anion that as a contamination from the water, and that was highlighted and C and EN few years back. So, next we have developed another compound that is also a hybrid compound. So, this is polyoxosiloxane with an amine functional group here, and this is a very famous dipeptide, diphenylalanine. So, this compound is very famous nowadays. Lot of people are working with diphenylalanine because of its hydrophobic hydrophilic balance. So, we have this peptide, and then we couple this compound with this peptide. So, now it is a hybrid material, organic and inorganic part both are there. So, initially we have studied that hybrid material with different spectroscopic techniques, and we figure out how the molecules self-assemble, what is happening in the self-assembly pattern, and we figure out that actually the molecules of the hybrid material are self-assembled in an antiparallel beta sheet manners, and there is intermolecular hydrogen bond and pi stacking interaction and all these things. But that is the theoretical background. In practicality, what we have seen that when it is only peptide, the compound is showing very nice hexagonal tubular structure. When it is only the inorganic moiety, polyoxosiloxane, this is very nice rhomboidal structure. But once you join them together, this is showing very nice, accurate or very close shape, this microsphere morphology. And these are obviously hydrophobic in nature now. So, we have just taken a paper and we coated the paper with this hydrophobic moiety, and now you cannot wet the paper. So, if you put the paper in water, again it will come. Without any water you cannot do that. And we have started by FESEM and also by load of the paper. So, the paper is now very stronger, and the paper surface is covered with all this microsphere of this compound, so making it very hydrophobic in nature. So what you can do with the paper, we have also started with that AFM, the surface of the paper, how it looks like. So now the paper can resist growth of any bacterial colony on the paper surface. So you can use this paper now for wrapping purpose, for packaging purpose, where you want that the water should not go inside and destroy your material, or it can protect your food or something else. So you can use this paper for packing purpose now. Other than that, so now this is iron nails. So we have coated half of the iron nails with our compound, the hybrid material, and we put that iron nails inside a chamber contain lot of water. So if it is a common iron nail, overnight there will be rust, and but when we put that coated part, the coated part is intact, but non-coated part, the rust form very easily. So now I can challenge that any raw iron I can protect it from rusting. So without any very difficult processing. So just coat with this material is completely colorless, you cannot differentiate between them, and you can protect it from rust formation. Not only that, so this is a silver artifact. So we know that if you use silver ornaments for few days, and then in a year there is hydrogen sulfide, the silver will react with hydrogen sulfide, it will turn black after few days. So we have covered this silver article again with our material, and now we use inside a hydrogen sulfide chamber, but nothing happened with the covered area. So you can protect your ornament from the silver sulfide formation. Even we have tried in a very harsh condition. So like we put it in the sodium chloride, potassium bromide, sodium, even in HCl. So when it is coated with HCl, there is no corrosion, but the uncoated part, it's corroded with HCl. So we think this compound is very effective to protect the materials from corrosion. And finally, we have used this compound as a fire retardant. So in 2014, my lab caught fire. Complete lab was damaged, there was nothing. So I lost about 3 crore rupees of instruments, and by that time I have 12 students. But I promised my student that I will take care, and I have taken care of them. And after that I have started this research. So I have little information that that polyoxosiloxane, it can prevent fire. And then when we have developed this thing, so this is just a mastic. So we have coated half of the mastic with our compound, and then without coating, the mastic is completely burning. With peptide only, the flame reduced, but mastic again completely burned. So with only pause, the polyoxosiloxane, it is reduced flame, but still the mastic is burned. But with our hybrid compound, it stopped at the point of coating. So we can take care of fire now with this compound, and we have patented this, and we have a collaboration going on to put this compound as a utility compound in market in future. Okay, so now a little bit difficult or different things. So this is also peptide mimetics, but now this is discotic peptide mimetics. So it's a disc-like compound, and for that purpose we have two kinds of central core. So one is this triamine or this tricarboxylic acid. And other than that, we can use this dicarboxylic acid amine or this monocarboxylic acid diamine, something like that. But the thing is that when there is 3 amine or 3 acid, this compound is C3 symmetric. If you replace one acid with one amine in a mixed kind of things, then you lost that C3 symmetry. So what is happening with this C3 symmetry? How this compound is behaving with change of symmetry? So there is some literature from this Boutalier group. So they have prepared this kind of compound and studied extensively using CD, and they propose that one and so forth. So we have developed this compound. with this benzene tricarboxylic acid, and we have replaced here the acid make a amide either with methionine or tyrosine. So from solution study we figure out that the compounds are self assembled in different manner. So when it is methionine, it's have something different than tyrosine. And then we got the crystal structure. So from crystal structure it's appeared that when it is methionine, still the CT symmetry is present. But when it is tyrosine, due to this large hydrophobic interaction, actually two of the tyrosine might be there in the one side of the central benzene ring, and another tyrosine is opposite side of the central benzene ring. That means theoretically the compound is CT symmetric, but practically you lost the CT symmetry. The compound is not CT symmetric in crystalline state anymore. And then we have check the central core area. So when it is CT symmetric, this amide bond, they are actually perpendicular to the plane of the central benzene ring, and that helps a threefold intermolecular hydrogen bonding interaction, and finally it forms a columnar structure through intermolecular hydrogen bonding interaction. But when it's lost the CT symmetry, now the amide linkage, they are in the same plane with the benzene ring. And though there are multiple amide linkages, there is no intermolecular hydrogen bond between the amide linkages. Rather than the one molecule is now surrounded by 6 other molecules, and it forms a cage-like structure, a porous structure. And then this is the packing diagram where it shows a honeycomb-like structure, and this is a porous structure. We have also studied with the AFM, and which shows that when the compound contain methionine, it's actually from a helical fibrilla structure, but when it's contain the tyrosine, it's a porous structure. And we have tested with the nitrogen, and we see that when it is porous structure, it can absorb up to 150 cc per gram nitrogen, which is quite high for an organic compound. So we can make a porous structure just by changing the symmetry of the discotic tricarboxyamine. And then again this is something we have played with the discotic tricarboxyamide, and now instead of aromatic compound, so we have placed with the aliphatic one. So now we placed beta amino acid and gamma amino butyric acid, so with this benzene tricarboxylic acid, and again we see that from UV visible spectra that it's following a J type of aggregation. And but when we studied in the gelation property, we see that when it is beta amino acid, so it forms a precipitate out of solution, and when it's gamma amino acid, it forms a gel in the solution. So everything is same, there is only one change with the CH2 group, and we are getting two different material properties from this compound. So again we have started with NMR and with this temperature dependent NMR, and what we have seen that yes, so when it is beta amino acid there is a different kind of packing, when it is gamma amino acid there is different kind of packing, and that's why it is showing different. So this is what we are saying. So when it is beta amino acid, so basically it is forming a fiber like structure, and that fiber further self assemble by entanglement. But when it is gamma amino acid, it's a straight fibers, and that is not entangled, and that's why we are getting two different structure. And okay, so this is the crystal structure for both this compound. Once again here for both the compound, the C3 symmetry is lost, so the two of this amino acid functional group is one side of the central benzene ring and another one in just opposite side of the central benzene ring. But somehow they manage to form a three-member intermolecular hydrogen bond stacking and make a columnar structure. And but in higher order packing, where we have seen that there is a honeycomb-like structure for the beta amino acid, but for gamma amino acid there is this hydrophobic interaction that actually helps to form that molecule gel in different organic solvent. which is missing actually in this case. And then again, this is another example where we have changed the core with triamine, but this core again it will help to form the gel in different organic solvent, and we have utilized that gel, and from different organic solvent what we get, the thickness and morphology of the fiber is differing from one solvent to another solvent. So it is not only the property of the material, but it is also the property of the environment, how you are changing your solvent, how the solvent is interacting with your molecules, and by that way the gel form. And here from the APSM again we see the very dense gel fiber. And then we have studied this gel. This gel is actually forming on sonication. So if you have compound, you dissolve in the organic solvent, you heat it, you cool it, the gel probably not form. But if you sonicate it, immediately the gel will form. And so this is we have studied by CD spectra how the sonication is affecting the backbone conformation for the gel formation. So basically what we believe that in solution you have much more flexibility than in crystal state. So though in the crystal the compound lost its Cth symmetry, but in solution when we are sonicating it, the compound get back its Cth symmetry, and then it helps to form the fibrilla structure, and which helps the formation of the gel further. And finally we have incorporated this lanthanide nanocrystals in the gel matrix, and we figure out that the lanthanide nanocrystals are finely self-assemble on the surface of the gel fibers, and we use that for a up conversion studies. And so this is something interesting, that with lanthanide nanoparticle and that is showing the up conversion. Now we have doped with a ketocyanin. So the lanthanide nanoparticle absorption is actually the emission of ketocyanin. So where ketocyanin is emitting, lanthanide nanoparticle is absorbing that light. So if we just check with a very small amount of ketocyanin and this lanthanide nanoparticle, actually we can arrest that up conversion. And so that is what exactly happening inside the gel matrix. But in solution state you cannot do that. So in solution state you have more flexibility, but inside the gel, so you can arrest the up conversion using ketocyanin. Okay, so now in a different story, so we have made an artificial enzymes. So this is the glucosidase. Alpha glucosidase, the main purpose of this, that it can work on uh, carbohydrates, and then it can chop the carbohydrates to monomer. So that is the what alpha glucosidase has done. And to mimic that alpha glucosidase, so actually we have developed this tetrapeptide, and that contain phenylalanine alpha amino isobutyric acid. That is a special kind of amino acid, and then leucine, and this is what actually it's a Hans ester. We have converted it into an amino acid. And now we have studied the X-ray structures of this compound. So it forms a hairpin like of structure. So where we have this two consecutive beta turn structure and followed by a 17-member ring structure. So that is the hairpin structure, a very famous motif in protein chemistry. And then we have used this foldamer in presence of iodine, and that actually hydrolyzing this carbohydrates. So for simplicity and to study by spectroscopic technique, so we have just used here this nitrobenzene. And what we have seen that in presence of iodine, just in 12 hours, this compound is chopping these ether linkages, and we are getting this nitro group, and that we can study with the spectroscopic techniques whether it is happening or not. Also, we have confirmed for mass spectrometry. But not only that, so we have studied with other carbohydrates, the real carbohydrates, and we see that our synthetic material is working well on the real carbohydrate also, as it is depicted from the mass spectrum. The main point is that, so once we have done this path, now what is happening to our compound? So the compound, if we go back, we will see, so there is a hydrogen, and now after this hydrolysis, actually this ring is going to be aromatized. So initially this compound has a angular shape, but when now this is aromatized, so this is just like perpendicular of the two aromatic rings to each other. And that exactly what happened here. So now the beta hairpin structure has lost, so it's a consecutive double bond structure only. Two consecutive beta turn are there, but now the third linkage has lost, hairpin structure has lost, and the compound is forming a honeycomb like structure in higher order assembly. So we can use a synthetic material as a parallel of a natural hydrolysis material. And then we have developed this molecular reactor. So the theory behind this is that we will devise a small channel, narrow channel, so where we can put our reagent, and we use that confinement to do the reaction further. And this is the scheme. So we have a nano channel, we will load component A, we will load component B, then we will give some energy, the reaction will happen, and we will get the product. So what is the utility? So this process can be effective for liquid gas or solid gas system. So advantage is this is completely solvent free, eco-friendly, it will be energy efficient, there may be some selectivity, and there is a safety and reliability. And so this will reduce basically the organic solvent. In chemistry lab we use a lot of organic solvent, mainly the chlorinated solvent, and finally we claim that we are doing green chemistry, but that is not the part. And simultaneously we cannot stop our reaction, then we will not get our cosmetics, our medicine, anything else. So the main theme was that, so can we do the chemical reaction using less amount of organic solvent or without any organic solvent inside a confinement. And then for that purpose we have designed this pentapeptide with phenylalanine and alpha amino isobutyric acid at the middle, so for phenylalanine. And we have got the crystal structure of the compound, so it's a 310 helical structure, completely helical structure. And if we put back the phenylalanine residue, so we'll see actually it's forming a pi channel, so which we can use as a confinement to do our reaction. And next question is it possible? So how we can do that? So first we have loaded toluene in the channel, and we see that two toluenes molecule is actually going inside the channel. So one is in the channel and another between intermolecular space. But toluene is not very reactive, so it's very difficult to do reaction with toluene. And then we have incorporated aniline. So again, two aniline molecule, it's just go in the crystal, and so one in the channel and another is the intermolecular space, and now the crystal is light yellow in color due to presence of aniline. And this is what the packing structure look like. And now we thought about the reaction. So what kind of reaction we can do with the aniline? So we can do a halogenation reaction that is very simple with aniline. Now the problem is that with the halogenation reaction it can be monohalogenated, and then it will be 3 isomer, or it can be dihalogenated or trihalogenated. So we do not have any restriction on the reaction. So okay, let us start with, and so first we have started with bromination reaction. And what we figure out that, so when we charge with bromine, the entire crystal structure just rupture, and we are very much frustrated that whatever our hypothesis is does not work. But we have analyzed that debris, and what we figure out that instead of monobromination, it is the tribromination that is happening. And due to this large structure of the tribromination, due to this effect, it's actually ruptured the system, the nano channel. Okay, so then we have done the iodination reaction, and now from mass spectrometry what we have seen that actually monoiodination happened, and our peptide is intact even after monoiodination. So we have so many aromatic rings in the peptide, but only the aniline is going to react with the iodine, and it's the monoiodination happened. And now the question is, so whether this is a ortho-iodo or para-iodo, so which form, if there is any selectivity. And what we figure out that though after exposure to iodine, the crystals are very, very bad in shape, so there are a huge amount of iodine just absorb over the crystal, but we just able to take data. The data is not very good, but we figure out the iodine, the ortho-iodination is taking place. Uh, this is because of this particular position of this compound inside the channel. And so we have done other reactions also using this kind of nano reactor, like this Diels-Alder reaction or this Morita-Baylis-Hillman reaction. So, and this is working fine inside the channel. Okay, and now I came to that gel part, so which is interesting. What now I am we are saying at that reaction engineering. So for most of the time, so our industry friends, so they said that whatever you are doing in the laboratory, that is very fancy. That's with very minimum amount of compound. You are using the chlorinated solvent, which is prohibited in industry, and we cannot use it in industry. So I thought, okay, so can we do something that we can do the organic reaction in aqueous medium and in a different way, so that the catalyst we can reuse again and again. And for that purpose, we have developed this peptide. So that's containing again meta-aminobenzoic acid. Here we have a natural amino acid, whether it is the glycine, alanine, or phenylalanine. And then at the end, we have C-terminus NN dimethylamine as the capping agent. The peptide we suppose to form this shield-like structure. It will form fiber, and fiber will form gel by restricting solvents. And then we thought, can we use the palladium nanoparticle inside the gel matrix, and so then the entire gel matrix can use for the cross coupling reaction, like Suzuki coupling reaction. And again, the concept is very simple. So we just put the gel at the bottom, so a layer of the gel at the bottom of a glass container, and then on top we add just aqueous solution of reagent A plus B in NaOH solution in water. And now if the gel is there and on top of there is the aqueous layer, we cannot use a magnetic stirrer. So we have to shake the whole reaction system. So it is second, not start. And so after the reaction at room temperature for mild shaking 5 hours, the product will form, and then we will just decant the aqueous layer from top of the organic layer, from top of the gel, and again we will fill up the aqueous layer with the reagent, and that cycle can be continued. So that is what we have planned. So from X-ray crystallography, again this compound that form anti-parallel beta sheet-like structure, and finally it forms the fiber, it forms gel in organic solvent. So during gel formation in toluene, so if we use the palladium acetate, the palladium acetate that will interact with the N and dimethylamine, and it will convert to palladium 0 to palladium nanocrystals, and that palladium nanocrystals will covered with the gel surface. So we have started without palladium and with palladium all the rheology and morphology of the gel. And now to how to utilize it. So this is the gel. On top of the gel, we add the aqueous mixture of phenyl boronic acid and this bromobenzoic acid in sodium hydroxide little bit. So that is our reaction medium on top of the gel, and the palladium are actually in the gel. And now we are shaking it with little bit for 5 hours, and so the boronic acid and bromobenzoic acid will react, and that will form the compound. And once the compound form, we just decant the aqueous layer, and we acidified the aqueous layer, we got back the product, and we separate the product by filtration, and again we can top up with the reagent and we can do the reaction. So we have done this reaction up to 5 cycles with almost 70% yield up to 5 cycles, which is not bad, because for every time when we are decanting, there is possibility of some leaching of the palladium nanoparticle from the gel matrix. and this is what the substrate scope. So we can do this with the brominated compound, with the iodobenzene, or with the pyridine unit as well. So we have a lot of substrate scope for this kind of reaction. So same catalyst we can use for multiple time. We can do the Suzuki coupling reaction at room temperature, and in mild condition without stirring, it's just a shaking, and we can easily identify the product simply by acidification and then filtration. Okay. And then this is my colleague Biplav Maji. So he has reported this reaction intermolecular d-aromatic 4+2 cycloaddition of naphthalene via visible light energy transfer catalysis. So initially when Biplav showed this result, I don't believe, because the naphthalene cannot do a Diels-Alder reaction. Here we have naphthalene, that is the aromatic stability. If it's going to do this reaction, then it has to lose the aromatic stability, and why it will go for that? But actually Biplav proved that it's happening. So with the photosynthesizer, and then in methyl cyanide acetonitrile, room temperature 24 hours with a blue LED. So this reaction is happening. This naphthalene derivative is reacting with this, going for a Diels-Alder reaction. From a two-dimensional structure, it is forming a three-dimensional structure. And what Biplav mentioned in his paper, so this is actually the stability of the transition state. So if you can make the transition state stable, then the reaction can happen. And how to make the transition state stable? Now, if you avoid oxygen. So actually for most of the reaction, oxygen is the culprit. So that's attack the transition state and that demolish the transition state, and that's why the reaction not happen. And so what Biplav used, they use very inert atmosphere to do this reaction. And then I said, and they have done all these optimization studies, and they have reported this. And then I think, so can we do this reaction without any inert atmosphere in a confinement inside the gel? So for that purpose, particularly we have developed this gel. So now the gel, there is no aromatic ring, nothing to absorb light. So with our gelator, we make gel. It's forming gel in DMSO, DMA, methanol, acetonitrile, kerosene, hexane, whatever it is. And then we have started with the rheology. So the gel is forming fantastic. So it's from the morphology, it's fibrous in nature. Also we have studied the melting point of the gel, and what we have seen that with increasing gelator concentration, so if the gel is very concentrated one, the melting point is going to be increased. And the gel has very good self-healing property. That means if the gel we cut in pieces and again we put together, they will self-heal, they will make a single bar or single fiber from the gel. And so then we thought, okay, let's do the reaction. So this is we have taken our gelator in acetonitrile, just to use that acetonitrile from our solvent purification system, and no degashing, nothing. And then we have used our material, all put them together with this catalyst, and then we just sonicate it. So immediately it forms gel, and due to this catalyst, so now it looks like little bit yellow, otherwise the gel is white in color. After 24 hours, 440 nanometer light, so the gel actually melt. And so we realize that something is happening with the gel. So we analyze and we figure out that yes, the reaction is happening. So say now this is open tube, so test tube. So it is open air. The so sensitive reaction is happening in the gel matrix, and gel matrix is working as a confinement to do this reaction. So we have started with all the rheological systems. So before incorporation of the reagent, after incorporation of the reagent, after the reaction, how the viscosity and rheology of the gel is changing. And then we have optimized with the concentration of the gelator, and we figure out that at 25 milligram per ml gel concentration, the reaction is happening very nicely. And under open air, we are getting 68% conversion, which is quite good. And so we have also optimized with the gelator concentration, and what I have said that at 25% gel concentration, the reaction is happening nicely. Again we have started with different solvent, and even now with methanol we are getting 60% conversion. So if you are just taking acetonitrile in solution, there is no product formation, but inside gel, even in methanol DMSO, we are getting a very good yield. And finally we have optimized wavelength, and we have seen that 456 nanometer is not working that well, but 430 nanometer light, the reaction is going very well. And so we have studied with the different substrate scope, and this reaction is happening with different substrate, almost 68 to 72 73% product in some cases. And then we have studied the morphology of the gel before and after reaction. So this is the undoped gel, so that is only gelator. And then with the photocatalyst and the substrate, so the gel is looks like that. After light irradiation, when the gel melted, so it looks like that. That means once the gel melted, basically our reagents are exposed to the air, and by that time oxygen is killing the reaction, and so we are stopping at 68% product. But if we can protect it maybe with some other gelator, or maybe with high concentration of gel, the reaction can go up to 90-95% of yield, because in solution state the oxygen will intervene and it will kill the activation state, and it will stop the reaction. And then this is the final one, so where we have seen this paper from Burkhardt Koenig group. So they have used organic semiconductor photocatalyst for bifunctionalize of arenes and heteroarenes. And basically this is the photocatalyst GC3N4, what they have used for this kind of reaction. And then the reaction they have done basically the cyclization and followed by the CF3 installation on the arenes. And so this is the substrate scope what they have seen, and this is what. And then in another group from China, so they have used the same catalyst, photocatalyst, for conversion of ethane to ethanol, just using hydrogen peroxide and the palladium particles inside the photocatalyst. So this is the GC3N4. We thought, so can we do this kind of photocatalysis with our gel system and do more or better reaction? So we have made that photocatalyst. We have studied with all the spectroscopic techniques, the state of the photocatalyst. Then we have made this gelator, again a different kind of. Similarly, this gelator, they do not have any aromatic system, so it cannot absorb light. It forms gel in different solvent like DMSO, DMA, methanol, acetonitrile. We have studied the gel with rheology, so the gel is very fine. Gel is also showing the self-healing nature, and this is the morphology of the gel. So it's almost like a Maggi noodles, so very much entangled gel fiber. The confinement are very good. So then we have done this reaction with help of my colleague Suresh Devarajulu. So the photocatalyst GC3N4, CF3SO2Na, 2 equivalent in acetonitrile and 456 nanometer BU LED, room temperature 24 hours. So the reaction is happening. So this is cyclization and followed by this CF3 installation on this part. So when this is in oxygen without gel, so there are almost no reaction. In open air, almost no reaction. But in presence of gel, we are getting 95% yield in open air. So that means oxygen cannot permeate through the gel, and the gel acts as a confinement, and gel can do this reaction, and we are getting 95% yield. So very clean reaction. If we compare from the previous one and this one, so in previous one a 2D molecule has converted to a 3D molecule, and due to this size exclusion actually it's ruptured the gel fiber and the gel melt to solution state, and then oxygen intervene and stop the reaction. But here there is no such three-dimensional molecule, so the gel fiber is intact, and so we are getting reaction with 95% conversion. So we have done with all the optimization with different photocatalyst, and what we figure out that GC3N4, that photocatalyst is working fine. We have also tested with many solvents, and acetonitrile we are getting very nice product, 94-95% yield, and this is what happening. So this is the gel containing the reagent, all the reagents, and after the light irradiation the gel is intact, and that's why we are getting 95% conversion. And so this is the morphology of the gel and the reagents before reaction, this is after reaction, so the morphology of the gel almost intact. And we have started with rheology before gelation, after gelation, and before doping, after doping with the reagent, and after irradiation of the light. And so this is the substrate scope, so we can do this reaction with many substrate, and that are giving very nice yield. Okay, so with confinement, now we can actually engineer our old reactions that need very sophisticated laboratory environment like glove box, like inert atmosphere, or any other sophisticated hood or something, but you do not need that at all. Actually, in an open table, if you have things, so just make a gel and put a blue light, you will get your product for all this sophisticated reaction. And so this is my research group, so who have students who has done this whole thing. And for financial support, it's CSIR, DST, Humboldt Foundation, and ISA Kolkata. And thank you very much for listening. If you have any question, I'll be happy to answer.
Any questions?
Yes, yes, sure.
They're very nice. On. Oh, it's on. Very nice gel work. So, what is the concentration you have to use in order for the gelation? So, a
So
percentage.
generally, if we report for only gelation, it is 2 milligram per ml, so
Yes.
which is very very less. Even
Yes.
for some gelator, it is 1 milligram per ml.
Yes.
But for this kind of reaction within gel,
Yes.
we have to use a higher percentage of
Yeah.
gelator.
Yeah.
Otherwise, though we claim that we are using UV light and we are using fans, so it is not heating, but even UV light heat your gelator, there some temperature increases
Yes.
and gel may melt.
Yes.
So
of course.
that's why we use a higher
Yeah,
gelator concentration.
you need a stronger
Strong
gel
gelatin,
for that.
yes.
Very
Yes.
nice. Very nice work. Thanks a lot.
Yeah, Devashish, very nice talk. I have a question regarding your breaking of gels, right?
Yeah.
So when you break the gels, do you see transition to colloidal system? Like, do you form colloids or crystals when you break the gels? Or what happens?
No, it's actually from gel state to solution state. So not colloid, so something precipitated out, and the acetonitrile is on top of that things. So that is what happening. And if something is soluble in acetonitrile, so little bit of gelator or soluble in acetonitrile, so it's that. So it's not a colloidal one.
Okay, thank
And it's easy to separate the product from the reaction inside the gel, because the gel is very very hydrophobic in nature. It's soluble in hexane and some hydrophobic solvent, and our product is not soluble in that. So you just use different solvent system, very easy to separate the product and purification. And if you can separate the product, you can reuse the catalyst for multiple times.
Sir, I'm Tiyasha Tiwari. I'm from Scottish Church College. Sir, you said that fiber is strong enough to contain web. So, spider-like web, when the compound is one side tyrosine and one side leucine, more than 20 degrees Celsius, it's a fiber. So below 20 degrees Celsius is less stable than
No, just reverse. So more 20 degrees centigrade, it's collapse. So it forms a liquid, viscous liquid. But below 20 degrees centigrade, it forms the fiber. So if you have experience to walking in the morning in a garden, mainly in the winter time, you will see in the early morning there are lot of this spider web in your garden. But at 8 o'clock or 10 o'clock when the sun rises, so everything disappears. So it is the same type of material. So at temperature above certain temperature, it will collapse and it will form a viscous liquid. But below 20 degrees centigrade, so it will form the fiber. And once it is fiber, it can take some weight, like the spider net. So the spider can move from one side to another side, or something big catch, it can be stuck in the spider net.
thank you, sir.
Yeah. Any more question? No? Thank you very much.